Now I want us to go together on two structural adventures. One on a continental scale, right through an orogenic belt, the Variscan orogeny, from here in Southern Ireland down into southwest England. And that will give us a big picture. But before we can see the big picture, we've got to build it up from lots of little jigsaw-like pieces. So the second adventure is to have a look at all these individual pieces. Just the sorts of things you'd be able to see if you went out and looked at outcrops near you. This is a normal fault. And in fact, the plane I'm lying on is the fault plane itself. Let me talk you through the main bits of this normal fault. The crack running through the face over there is the actual line of the fault seen in section. And you can see that it's a dipping plane. It's dipping steeply to the right. And rocks are displaced from this side to that side. There's a very clear, thickish black shale bed on the left, displaced down to the right-hand side. Now, how do I know that's the same bed? Well, I know it's the same bed if I try and match the exact sequence of beds in this side, which is the footwall, with the sequence in that side, which is the hanging wall. Just have a look at the sequence in the footwall. Thick black shales, 2 or 3 thin sandstones, that's there, 2 or 3 thin sandstones, and then 3 or 4 very thick sandstones underneath. Now, if I go across to the hanging wall side, here I can see the thick black shales, the 2 or 3 thin sandstones, and underneath me here, the 3 or 4 thicker sandstones. This sequence in the hanging wall matches that one in the footwall. This side has been displaced downwards relative to that side. Now, let's have a look now at the fault plane itself, which is this very surface I started off on. Here it is, the fault plane itself, and on the fault surface there are these almost vertical lines coming down there. There's some more over here. Now these are called slicken sides, and they're an excellent bit of evidence for the way the fault moved. These are sometimes grooves and sometimes mineral fibres that have grown in response to the hanging wall moving over the footwall. And as it moved down, these things were generated. Now they're directly down the dip of the fault plane, so this must be a dip-slip fault. The hanging wall has slipped down like that. And one final point. We also know that the fault has stretched the crust horizontally. Because if we look again over at the black shale, we can see that there are places where the black shale is very thin or even missing right in the core of the fault there. You could drill vertically down at just the right point and miss the black shale bed altogether. So the beds have been stretched out horizontally. And that's one of the things that normal faults do. They displace the footwall downwards and they stretch the crust horizontally. And this is actually oh so typical of normal faults. They don't come in ones like we've just been seeing, they come in 2s or 3s. Here's one going down through there, this block thrown down compared to that. I can trace it down below and it meets a friend coming down here, look, again with a down throw. And the two of them join together and go right to the bottom of the section. But there's a sting in the tail here too. Look at the overall picture. This is actually a limb of a very tight fold. Now when rocks have been shortened this way, as much as these have, they've got to stretch that way to accommodate that shortening. And here's the evidence of the stretching, these normal faults. Now this is a different type of fault. It's a thrust fault, a low angle reverse fault. You can see the plane of the fracture cutting diagonally through the beds from the top left-hand side down to the bottom right-hand side. Look first at the footwall. That's the block of rocks underneath the fault plane. These beds are unfolded, but as you follow them from left to right, you see that they are actually cut out by the plane of the fault itself. Now let's have a look at the hanging wall. Well, the beds here are quite clearly folded. There's a very tight fold in the hanging wall. Different amounts of movement along different sections of the fault produce folding. These folds form dominantly but not exclusively in the hanging wall of the fault. This simple model pins the hanging wall and footwall together at the left-hand end of the section and allows slip at the right-hand end. Small amounts of shortening cause an open fold to form ahead of the thrust, with the fold axis parallel to the thrust tip line. By and large, the fold axis lies approximately at right angles to the fault slip direction. As slip increases, two things happen. The thrust tip propagates forward, whilst the extra shortening in the hanging wall block gives rise to a tighter, greater amplitude fold. Usually this fold develops a flatter axial surface, becomes asymmetric, and often carries a cleavage. Eventually, as deformation proceeds, the thrust tip propagates right through the fold pair. Typically, the inverted limb is severed, and the hanging wall anticline is displaced away from its syncline. And here's a good example on the coast at Tor Bay. And this little example of a thrust, I think, makes several points very clear. Here's the thrust plane, look, dipping away at a shallow angle down to the right-hand side of our view. This is the footwall, and up above the thrust is the hanging wall. And look at the beds in the footwall, they're cut off one by one by one by the thrust. And here in the hanging wall, there's a fold, just like in our first example. And down on the top, I can see slicken sides, which are showing me the sense of movement, which is top to the left. Now, not all structures tell a story of shortening or stretching. Some of them show that bodies of rock have moved laterally past each other, and there's a good example right here. Let me show you how this little zone shows that blocks of rocks have moved. This piece has moved in a direction relative to that piece, like this. Point of fact, we don't know whether that one moved or this one moved this way, so I ought to have a shear couple in. And that's a zone of deformation. Now, how do we get these quartz-filled veins from a shear couple like that? Well, a little experiment should convince you. Here's a block of paper, and I'm going to displace the whole block in the same direction as that shear couple. And I've started with a circle, it's undeformed. Now, I'll shear over the block of paper. There we go. Notice that the edges of the paper block have moved in the same direction as the arrows, and how the circle has turned into an ellipse. Right, let's put an ellipse down there to sort these things out. There's the ellipse that we made from our shear deck. Here's the circle it started from. Now you've noticed that to get to the ellipse shape from the circular shape, you've got to stretch it in this direction. Now, more props, let me put the pen down in the stretch direction and remove these things. Now that's the stretching direction, and can you see how the cracks have opened up in this stretching direction? The rock's been pulled apart, forming a crack. Now there's more shear in the middle than there is at the edges, so if you follow each part of the vein outwards, the veins get narrower and narrower and eventually disappear. Now we still don't know whether this block moved that way or that block that way, but we do know that this zone was formed by that shear couple. Therefore, it shows us that bodies of rock have moved relative to each other sideways. And sometimes you see evidence that the bodies of rock have moved enough to create a fault. The old head of Kinsale lies right in the south end of County Cork, in the Republic of Ireland. And here at Old Head, there's a lovely small-scale example of our third type of fault, a strike-slip fault. And I intend to show you that it is a strike-slip fault now. You can see the fault line, it's this crack through the rocks, and individual beds here end at this crack and pick up again in a slightly different way. The fault line itself is filled, as they often are, with odd pebbles and boulders and water, in this instance, down by the sea. And in the very prominent yellow mudstone bed here, we can see the trace of bedding coming along into the zone, and it sweeps around and into the zone here. And then on the other side, under my feet, again we see bedding, and that sweeps around in the opposite sense as we get into the exact plane of the fault. The fault is steep, dipping steeply into the ground. Now, I want to establish first off how we know that it's moved sideways, and the answer really lies in comparing what we see down in front of us here with a paper model. Now, let me get out the paper model. Now, on the edge of the paper here, we've got two symbols, a circle, and we've got a straight line which is at right angles to the edges of the paper. Now, let's turn that parallel to the fault, and I want to shear it. It could go either way, but let's shear it this way. Now, we can see that the circle has changed to an ellipse, and the line has rotated. It's no longer at right angles to the edges, it's rotated clockwise. And there's some evidence for that happening here in the rocks, because we can see bedding in this very clear yellow mudstone sweeping round and into the fault zone. And the mirror image of it on this side, under my feet, bedding sweeping round that way. And that shows actually that I must have got the right sense of shear first time. It's sheared this way to make bedding sweep round on that side, round on this side. So I should actually use that strain ellipse, and I've got one here we'll put in. That's the right sense of displacement for the strain ellipse, and that's created by a shear like this. So that's the sense of shear of this fault. It's a dextral shear, and so the thing must be a dextral or right lateral strike-slip fault. And there's one last thing we need to establish now, and that's how much displacement. Now, it looks at first, doesn't it, as if this yellow muddy bed matches across the fault zone. There's been very little displacement. But I don't think that's the case, and I'm going to prove it to you by looking at the sequence of rocks on both sides. Let me put one of these white arrows down here, just at the very top of the yellow bed, just as a marker arrow. And now let's have a look at the sequence up this side. The yellow bed, a brown sandstone, and quite a thick yellow mudstone, and two distinctive brown sandstones. And let's try and match this sequence on the other side of the fault. Well, I'll go across here. I think this is the first of the two top brown sandstones, and it's very slippy, so I'll try not to fall over as I come through here. Then the rather thick yellow mudstone, then the brown sandstone on top of it, and here's the same yellow mudstone as I started on that side. So it's not a match across there at all. There's a displacement of about 2 meters right laterally across this fault zone. So that's our three main types of displacement on faults. Down dip displacement for normal faults. Up dip displacement for thrust faults or reverse faults, same thing. And this lateral displacement on strike-slip faults. Now, this is a really interesting little piece of structure out here on the North Cornwall coast. It's a duplex. And it's a device for making the rock shorten and thicken. And I'm going to show you just exactly how it does it. Look at the sequence of rocks that I'm sitting on here. There's quite a prominent sandstone bed underneath me, and a sequence of beds up here, which are dipping away gently to the left. Quite an obvious sandstone bed up at the top, and some thinner ones in between. But this is the bed that we're really interested in. This is the bed in which all the fun happens. Let's just follow it a bit and check how thick it is. Now, the thickness here is about that. It's about 35 centimetres thick here. But when I work my way over to the right, right through this piece of the bed here, until we get to the maximum development of the duplex, the same bed, and you can check it from the sequence above and below, the same bed is now over 1 metre thick. Why is that? Because the rocks have been shortened this way and they've had to thicken vertically to accommodate it. Now, how far does the duplex extend? Let's go and see. Now here at the far end, there's the bed underneath the duplex. There's the thickened bed. And it's back to its original thickness. Now, let's go and see how this happened. And while I'm walking back, you check out the sequence of beds. We need to start again right at the beginning. The bed has shortened this way and thickened this way by a combination of a set of faults and folds. And we need to just see where these are now. Here's the first one. That's the first fault. It's a low angle fault, and it's a thrust actually, as we'll see in a minute. And the second one in here, and the third one in here, and so on, 4, 5, 6, lots of them, thickening the duplex up. Now, what do these look like in detail? Well, come in and I'll show you. This is a typical fault within the duplex. Dipping at about 40 degrees to your left, it extends right down here to a fault that goes along the bottom of the duplex. How do we know this is a fault? Well, we can see the slicken sides here. We can see those little veins and grooves that show that these beds have moved relative to those. And if we trace it up to the top, up here, it meets another fault in the roof. And that's got slicken sides on it too, so that's moved. And this one here has also got slicken sides on it. And I can see that they're aligned down the dip of the thrust plane. So this block has moved up or down, we don't know. How can I tell whether it's a thrust or not? Well, it's a thrust if it doubles beds up, if it duplicates beds. And here I can trace beds in the top. They're cut off at the fault plane here. And those same beds are repeated here in the footwall. Have a look in the footwall here. There's a bed with these fine features, and then a centimetre thick dark bed, and then a very clear lighter bed. Now let's see if we can match them up in the hanging wall. There's the features, the dark bed, and the clear lighter bed. The sequence has been repeated. You could see it twice, once in the footwall, once in the hanging wall. So that means it's the thrust. About 45 centimetres of displacement from here to here. So that's copper-bottomed evidence for this being a thrust, and if you do it with all of them, they're all thrusts, and they've all contributed to the shortening. Now, one last piece of evidence I want to show you, and that's there are broad open folds here associated with the faults. Can you see the curve of this bed round here? This curve, it's a fold, It was formed by the hanging wall block moving up and over the footwall block. And each one of these elements in the duplex, they're called horses, each one of the horses is folded. The duplex grew by the first fault forming at the left-hand end and successively younger faults forming to the right. And as each one moved, it folded its hanging wall. Duplexes form at thrust ramps. That's places where the detachment plane steps up from a lower to an upper level. Folds form and beds thicken above the step-up, caused by movement of the fault. Movement direction is shown by the slicken sides. The process of vertical thickening and folding eventually reaches a limit where it's mechanically easier to generate a new ramp than it is to continue moving on the old one. When the new ramp forms, the movement on the old one stops. Part of the old footwall becomes incorporated into the hanging wall and therefore starts to deform. Continuous movement of the hanging wall block is accommodated by a cycle of ramp formation, vertical thickening and shortening, folding, and then new ramp formation. And just to round it off, here at the extreme left-hand end is a mini duplex. In this shaly bed underneath the sandstone bed, that whole process is repeated on a much smaller scale. It's a scale of 1 metre here with lots and lots of little thrust faults through it, rather than the tens of metres in the sandy bed. Now, taken together, this is a fabulous duplex. It's probably the best one you'll ever see, and it's certainly the best one I've ever seen. It's wonderful! Now, I suppose in some ways it might seem rather obvious, but we must always bear in mind that folds are three-dimensional structures. We often look on the map view down on them. We often look on the side view in the cross-section, but every single thing we see is three-dimensional, like these out there. And these folds are about as geometrically straightforward as you're ever going to get. Come and see. Nice little folds, wavelength of a couple of metres, outcrop scale. These are straightforward because they're open folds, that's the limb dips are not very great. They have steep axial surfaces, they're upright, and they have very gentle plunges, they're about horizontal. Now, although that's the simplest situation, you'll also find fold axial surfaces that are inclined or even flat-lying, fold axes that are tilted so that the fold plunge varies from horizontal through moderate plunge amounts to the vertical. And the fold shape, that's the angle between the fold limbs, changes from open to closed to tight to hairpin-like or isoclinal folds. But it's often in fold profiles like this that we get the most structural information. Now, we can see two distinctive ways in which these rocks have shortened. One is the folds of bedding, and these lines here are beds, and we can see they're quite tightly folded into a syncline. And I can define the axial surface of this syncline if I join up the places of maximum curvature of the beds, here and here, for example, and here, and so on up the fold. So the axial surface is almost vertical on this fold here. But if we look both in the limb area and in the crest area, we can see the trace of rock cleavage in there. Here it is, coming down almost vertical as well. Well, the cleavage is very clear here, but it's even better further up, where you can see it both in profile and on the bedding surface. Now, the fold itself has been formed as the rocks shortened, and it has a vertical axial surface, so that's horizontal shortening. But the cleavage too has formed when the rock shortened. The two processes are genetically related. The folds and the cleavage formed at the same time. Near Porthleven on the South Cornish coast, there's a superb section, absolutely full of structural detail, and it's really clear to see. As long, of course, as you get the tide right. One of the smashing things about these rocks here at Porthleven is that they're very clear. They're an alternating sequence of light-coloured siltstones and dark-coloured mudstones. Centimetre by centimetre, the beds change, so we can see the structures really clearly. And in this little area here, we have some excellent evidence, really first-class evidence, for just how much the cleavage is a shortening direction. Have a look at this little white vein through here. Where it's going at right angles to the cleavage, you see the cleavage that way, where it's at right angles, it is incredibly tightly folded. Lots and lots and lots of tiny folds. An immense amount of shortening in that direction. Yet where this vein happens to swing round at a much more acute angle to cleavage, then here it's almost not shortened at all. That's because, imagine the strainer lips looking like that. It's shortening a lot across the cleavage, but actually stretching in this direction. These folds are lying on their side, but they're still the product of shortening, and their cleavage, which is very, very clear here, is still more or less parallel to their axial plane. Here's a very clear fold, look. There's another bed. We could define the axial plane parallel to the dividers. And let's have a look down here all the way through the axis. That very strong parallel alignment there, which is the rock cleavage. Both the very tight folds and the very strong cleavage in these beds show just how very, very deformed they are. We could even have a very rough estimate here in the field about how much shortening this light-coloured bed has experienced. What we need to know is the present-day dimensions between, say, some point on this fold here and somewhere else, say there. Measure that distance across and measure the distance round the arc length. Now, measure the distance across first. I've got a ruler and a pair of dividers to help me here. Let's put the ruler across that point. And it's about, very roughly, 20 centimetres present day length across the cleavage from one limb through the fold pair to another limb. Now that's the final shortened length. Now let me set the dividers at 10 centimetres and go from the same point round the arc. 10, 20, 30, 40, almost 50 centimetres round the arc length. So as a rough estimate, we've got 20 centimetres of present day shortening across. The bed was 50 centimetres long, and so we can work that out. That's 20 minus 50, which is minus 30, divided by 50, which is 3/5, which multiplied by 100 comes out at 60% shortening. The minus sign tells us it's shortening. Well, mathematics apart, the answer is that the cleavage and the bedding have shortened by 60% across here. So we see that no matter what the orientation, folds and cleavage both show the effects of shortening. It's very common to find folds and cleavage genetically related like this. The cleavage planes oriented parallel, or almost parallel, to the axial planes of the fold. But not always. In uniform sequences of sediments, you often find rocks that show good cleavage but no folds of bedding. Like this outcrop here. Here's bedding, no folds, and here's cleavage, a bit steeper than it, pervading through the whole of the rock. And so uniform is the cleavage in this outcrop, and so homogeneous the rock sequence, that they've been quarrying slates here for many, many years. And slates from here in Valentia Island, in the extreme southwest corner of the Republic of Ireland, have been exported to make bases for snooker tables, for example, and to roof even the Houses of Parliament in London. Cleavage forms best in rocks with a high percentage of platy minerals, typically mudstones. The process is a dual action one, involving a physical rotation of grains coupled with a chemical effect, mineral growth or dissolution. As deformation progresses, platy minerals physically rotate towards alignment. The most stable configuration is with the flat faces at right angles to the maximum shortening direction. Most platy minerals also grow by adding material to the edges of the plate rather than by adding new layers, and they dissolve in the same way. Now, the pattern of deformation within the rock favours the growth of grains aligned at right angles to the shortening, and the dissolution of grains aligned parallel to it. The more shortening, the more perfect the cleavage becomes. And how do we ever know how much strain is involved in rock cleavage? How much shortening there's been? Well, there's some excellent evidence right in front of me, on this bedding plane. Now you can see beds, they're very clear. There are these layers underneath me, variable thickness. In fact, these beds have ripple marks on them that show that water's flowed over the surface. But the piece of strain evidence is right in front of me, it's a fossil. The marks here are the marks left by the forelimbs and hind limbs of one of Europe's earliest amphibians as it walked across this bedding surface. In fact, I'll have a go and see if I can match what it did. Something like this, 4 very primitive limbs that it moved a sinuous way like this, stepping across. A bit smaller than me, only a metre long, and it just went all over the place. Goodness knows why. So clearly the animal wandered all over this surface to become a bedding plane, and presumably it did so with a fairly even stride like I'm doing, and of course with the same footprint every time it put its forepaw or its back paw down. How are we going to use those to work out the strain in the rocks? Well, it's quite a long and involved story, but let's go through it piece by piece. This is the bedding surface, and you can see the trace of cleavage going along the rock like this. Now, what are we looking at? Well, we're looking at this bedding surface in red and the intersection of a steep cleavage plane, making a linear feature along the bedding surface, the trace of cleavage on bedding. Now, let me represent that with a line. So that's the cleavage trace. Now, we believe the cleavage represents a shortening across its trace, something like this. Squash it together, right angles to the trace, and of course you would turn any shape that was originally a circle into an ellipse. So the rock has shortened this way and at the same time stretched that way. Now, what effect would this have on the trackway? Well, the stride length should be shortened in this orientation and stretched in that orientation. And that's what we see on the track. And the footprint should be different too. An original footprint that was, say, an elliptical pad put down in this orientation should be stretched to make a more elliptical pad mark, like that. But of course, if it were put down in the other orientation, like that, it would be stretched out here and become more circular. Now, that's what you would predict. Is that the case? Let's have a look. One's over here, where the trackway is going across the shortening direction, should become more elliptical. Let's have a look. And there we are. That one is more elliptical. Now, further round here, where the trackway is turned through 90 degrees, these should become more circular. And surprise, surprise, they are. Well, okay, that's what we would expect to find, and that's indeed what we see. Now, the next bit is mathematical, and we don't need to go into details, but we can use these shapes and orientations to show that the cleavage shortening is about 50%. And that means that lines in this orientation are now half the length they originally were, whereas lines in that orientation are stretched very much longer than they originally were. Trackway deformed, trackway undeformed. Now, a very important point is that different materials behave in different ways, even if you do the same sort of thing to them. It depends on their physical properties. Watch. Now, rocks behave just that way as well. Here there are sandstones and shales. The sandstones are competent and they break when they're stretched. The shales are less competent and they flow when they're stretched. So we see cracks filled with quartz in the sandstones, no cracks in the shales. Now, these superb folds also show the same sort of problems. They're different materials as sandstones and shales, and the sandstones are behaving in a much more competent way than the shales. Let me make those folds with these pieces of foam. Doesn't matter when I shorten them, they can actually form an anticline like that, or a syncline like that. They're both responses to shortening, and the competent sandstones behaves rather like this foam. But the shale has to be quite different. That has to flow and occupy the spaces that the sandstones have made form, just like the toffee in the Mars bar does. Just look at the amounts of movement of shale into the core of this structure to fill the space between the sandstones. This is a cliff-size fold at Widmouth Bay, but the same thing happens on a much smaller scale too. Just have a look at the shape of this particular fold area here. Look at the shape of the outer arc of the fold and the inner arc. Very different and characteristic of an extremely competent bed shortening when it's surrounded by incompetent material. If I have this piece of foam here and shorten it from top to bottom, which is more or less mimicking what's gone on in these rocks, you can see the foam folds, and the more and more I do it, the more and more we match the shape of that particular bed. The foam has a rounded outer arc and a very pointed, tight inner arc. That's because the foam is much more competent than the air that surrounds it in this particular model. Now, these folds, this one in the foam and back again to the one in the rock, retain their bed thickness all the way around the fold, and I can show this. Let's set my dividers to measure the thickness in this part of the limb here. And then I'm just going to check the fold thickness. And here, about the same. Right in the crest, the same. Further round, just about the same. I'm pushing my luck a little bit onto this limb. Well, it's a bit shorter there. Of course, nature has a few tricks up its sleeve every time. Now, we call this shape a parallel fold, and over there there's a similar fold. Now this fold here, it's actually the one we were measuring the shortening around earlier. This is a good similar fold. Now, similar folds don't maintain their bed thickness all the way around, and I can show that. Let me set my dividers to the bed thickness here and measure it all the way around. A bit further around. I'm keeping this one on the inner arc, but by the time I've got into the middle, you see the bed is actually thickened a great deal. And if I go around, it's back to its original thickness on the other limb. Now that change of thickness is the essential thing about a similar fold. Actually, the thickness parallel to its axial surface, which is along here, is maintained all the way around. And I can show you that too. Set the thickness with the dividers parallel to the axial surface and keep the 2 points parallel to that direction all the time. Keeping them on the bed top and bottom. Well, not quite exact, but not bad, and the same the other way. And to wind up our study of cleavage and folds, something completely different. Now, it's not always as clear as you might think which are anticlines and which are synclines. It's fine when they're like this, because the upfold is clearly an anticline and the downfold is clearly a syncline. But what about when the folds lie on their side like they do here? Which is the syncline? Is it that one or is it this one? Well, to sort it out, we need to use some other piece of evidence. Now, magically, look at it this time. Here I have an anticline and a syncline with the red bed on the bottom and the blue bed on the top. The red bed is older and the blue bed is younger. I can tell that this is an anticline because of its shape, but also because there are older beds in the core, whereas the syncline has younger beds in the core. Now turn this on its side, and I can tell which is going to be the anticline by the exact same way. There's still older beds in the core of the anticline and younger beds in the core of the syncline. And the intervening limb is actually upside down. The beds are getting younger going downwards. Now, what better example than this one here? This sandstone is older than that shale. I can tell from the detail of the sedimentology in the bed, and I can tell from the irregular base of it. So this whole sequence is almost upside down, getting younger that way. So, if the situation was like this, and the beds were upside down in this middle limb like they are here, I would expect an anticline up above me and a syncline down below me. Now here's a pair of folds. Which is the anticline and which is the syncline? How are we going to know? Well, the answer is in here. This fold closure here is folding a light sandy bed set in a darker muddy matrix. But have a look at the colour of the bed as we go this way. It gets darker and darker and darker. There's a gradual change from that part to this part, whereas the other way there's a very sharp change. So that tells me that this is the base of the bed and it's getting finer and finer and finer towards its top. So that is the base, that's the top. That bed must be younger again. So the beds are getting younger into the core of this fold, so it's a syncline. To unravel structural histories, we mustn't look at pieces of evidence in isolation. To see the more complicated picture, we need to use every clue, like we've just done. It's easy to be misled. Here's something you saw earlier. It's a low-angle thrust. Or is it? There's just one slight snag. As is so often the case in structural geology, things are just not what they seem to be. Now, the thrust behind me is an early structure in what is really quite a complicated sequence of structural events. The beds have shortened right enough, as they must have done with a thrust quite like that one, but then a second event happened. The rocks were folded into these enormous folds that make up this cliff. And so the thrust plane itself is not only tilted up to be quite steep, but is actually folded along with the beds in these folds. So far, we've seen individual structures. We've seen folds and faults, and we've seen structures that allow the crust to stretch and to shorten and to slip. But we want now to put these all into a context. There's no accident we've come to see all these structures we've shown. They're all part of the Variscan fold belt, which occupies the southern part of Ireland and the southwest part of Britain, right down as far as Cornwall here. So now we want to go in a traverse through that belt from the Midlands of Ireland down to the south coast, and from Somerset down through Devon into Cornwall and right down almost as far as Land's End, putting the whole into a context. Geologically, we'll be looking at two particular broad areas of rock. The youngest of these, which we've coloured in blue, are sediments that were deposited between 300 and 350 million years ago. We call them Carboniferous rocks. And in Ireland, in the Burren in particular, they're marine limestones for the most part. And then we'll also be looking at our second group at slightly older sediments, coloured in pink and deposited between 350 and 400 million years ago. These are known as the Devonian. And in southern Ireland and South Wales in particular, they're red sandstones, red siltstones and red mudstones. Over in the west of Ireland, in the Burren, the Carboniferous limestones are scarcely folded. They've been uplifted because they were formed under the sea. Those Carboniferous limestones form big, extensive sheets, but there's no major faulting, there's certainly no cleavage. Very little strain and very little shortening. Now, in central Ireland, we see the big oval outcrops that are rimmed by pink Devonian rocks and have in their core green, older rocks still than that. Over in the east of Ireland, we can see that there's a mass of green rocks. They're older, and actually we're just going to ignore those from now onwards. And down in the southern part of the Republic of Ireland, in the counties of Kerry and Cork, there's a very interesting set of long linear bands of alternating pink Devonian and blue Carboniferous rocks. Now, why do we get this variation of rock type at the surface? Well, we can eliminate topography, because at this scale the topography is insignificant. What it must be is structures folding and faulting. Now, if we put on a structural overlay onto the map of Ireland, we see immediately what all these features represent. The big oval outcrop areas are folds, and of course they're anticlines because they have the oldest rocks in the core, and they're bounded to the north by steep reverse faults. Further south, the area where there's Devonian rocks almost completely at the surface is south of another major reverse fault line that goes from Dingle Bay through to about Waterford. And then further south still, 5 to 10 kilometre spaced anticlines and synclines, trending approximately east-west and bringing Carboniferous rocks to the surface in the cores of the synclines and Devonian rocks to the surface in the cores of the anticlines. And are there any structures like this over in the UK? Well, yes. Let's go over to the Mendips area south of Bristol and see what's there. Here we are in Somerset, on the north side of the Mendips, in Burrington Combe. Vast thicknesses of Carboniferous limestone dipping away to the north. The point is the scale. To get to southerly dipping rocks like these, we've had to come 5 kilometres south of Burrington to Cheddar Gorge. This is a really big fold. Now, if we could see a cross-section through the Mendips, it would look very similar to this. It's an anticlinal fold, asymmetric, overturned to the north. The steep northern limb at Burrington Combe might look a bit like this. The gentle southerly dipping limb at Cheddar might look like that. In fact, it's exactly the same as this fold, except of course that it's 10,000 times as big. And if you're still not convinced, we can even make a mendip with a piece of felt. But how do we know when this happened? Now, this is the best geological evidence for the timing of deformation. It's an unconformity. We're back on top of the mendips, and you'll remember the folded limestone sequence. Well, here's the same limestones underneath this plane. They're folded, but the beds above the plane, they're younger and they're not folded. So the folding must have taken place after they were deposited and before they were deposited. And we can cross-check these on the map. Here's the big, broad, blue sweep of the Carboniferous rocks in a plunging anticline. It's an anticline with the older Devonian rocks in the core. And then last but not least, the post-Carboniferous rocks sitting unconformably on it, tracing a sinuous junction all the way around the northern limb of the fold. But how does this fit into the wider picture of South Wales and southwest England? Now, in the extreme west of Wales, the rocks are quite old, older than our Devonian, so we'll ignore them as well. But if we look into the South Wales area and the South Wales coalfield and out towards Bristol and Somerset, there's our old friends, the pink older Devonian and the blue younger Carboniferous. And here, sitting on top of the unconformity throughout much of Somerset and places eastwards, are younger rocks. Now, Devon and Cornwall themselves. Devon's the home of the Devonian, you might have guessed. They're Devonian rocks and three new rock types. The bright red blobs of the Cornish granite batholith. And two more rock types, special here. The greens of the old metamorphic rocks down in the Start and the Lizard peninsulas. And then a very different rock type, oceanic crust, emplaced onto the continent here in the Lizard in this bright orange colour. And here's the geology map with the structures overlaid on it. And we can see all the same sorts of structures as we saw in Southern Ireland, but with a couple of interesting additions. There's the unconformity, where the younger rocks sit on the Variscan rocks. And there's also strike-slip faults. They're at a much steeper angle than the basically east-west folds and faults we've been looking at in Ireland. That's lateral movement of blocks. In particular, one that's postulated. That means we don't really know it's there, but it goes through the Bristol Channel and out under Southern Ireland. Now, all these structures, the thrusts, the folds, the strike-slip faults, they're all part of the Variscan orogeny. And we know when that happened. It must be younger than the Carboniferous because it affects them. That's younger than 300 million years. And it must be older than the rocks above the unconformity. And they're about 250 million years old. So it must have happened in that 50 million year window. Now, how do the structures vary? Well, that's much easier to see if we look at the cross-section rather than at these maps. So, on magic carpet travel north to south through Ireland, past the Burren there and the big anticlinal folds, across into Valentia Island where the Devonian is at outcrop, and right down through County Cork to the south coast of the Republic. Now, I think we'd better see that a bit slower, so back we go to the north again. Now, back in the north end of the section, up in the Burren up here now, very gentle dips, very long wavelength folds, very low amplitude, no cleavage in these limestones, about 2% shortening. Yet further south down there, over at Slieve Mish, limb dips are much steeper. There's more shortening, about 7%, but still no cleavage. Let's go on southwards. And in Valentia Island here, those open folds on the shoreway, about 50% shortening in the cleavage at the trackway, remember, and then the very good development of the slate in the slate quarry area. Now, by the time we've got to Old Head over there, you'll remember seeing folds asymmetric to the north, strong axial plane cleavage, more and more of them out towards the south coast of Ireland. Now let's go off and see how this compares with the UK section. Off we go. So now north to south through the UK, through the South Wales area, Pembroke, up over the Mendips and down into the Bristol Channel, cross there into North Devon, and here comes the big granite batholith from Devon and Cornwall, and all those funny structures around the South Devon coast, and the lizard. Now let's go and have a look at those in some detail, shall we? Off we go! Now the situation in Brecon up there is about the same as we had in Ireland at the Burren. Very gentle dips, very little strain, and yet on over towards Pembroke we cross the thrust front and suddenly find folds and cleavage developing, just like in Ireland. Now onwards, southwards, further on. Now here's the Mendips up here. We've just seen them now, overturned folds, overturned to the north. Those limestones are folded, no cleavage in the limestones. Down beneath me, look, is the Moho. We're looking at a section right through the crust here, and on over there's the Bristol Channel, where we've got to the postulated strike-slip zone where Devon is moving towards us. Now, let's go on into Devon. Now, the main feature in Devon and North Cornwall is this large syncline in carboniferous rocks at the surface, but the structures are really, really complicated. This is the sort of thing we saw at Widmouth Bay with the duplex and the thrust on its side. And by South Devon down here, the structures are really very complicated. Over at Torquay, at the Hope's Nose, there's flat-lying folds and thrusts. Around at Porthleven, further south than that, we've got extremely complicated tight folds with folded cleavages. And then above that again, there are the naps which contain metamorphic rocks and the ocean crust rocks at the Lizard. And after, later, but part of it, the great granite batholith of Cornwall. My goodness, it's 12 o'clock and the magic's running out. I'm out of here. Now, what do I want you to get from this section? Well, there are 4 key points that are really important. First, just look at the scale of these structures. There's no vertical distortion here. These really are crustal scale structures, interpreted from information on maps and modelled on the small scale structures we've seen in the field. Second, see how these structures affect not only Devonian and Carboniferous rocks in pink and blue, but also older rocks too. Everything's caught up in this late Carboniferous to Permian deformation. Third, look at the asymmetry of the structures. Most of the folds are overturned to the north, and most of the thrusts displace their hanging walls northwards. Both of these reflect the fact that the driving force of deformation lay at a plate boundary well away to the south of Britain. And lastly, notice how the intensity of deformation increases southwards, both in Ireland and here in Britain. The rock successions that were nearer the plate boundary in the south were deformed much more intensely than those that were deposited further north. Now, we've one last thing I want you to consider, and it's based around the timing of this deformation. I've got a very sophisticated but simplistic computer model here. Just watch it. I'll set it going. Now, let it run through first. Come back to what it all means next. That's the present day situation. The rest was how it developed. Let's go right on back to the beginning and look at it bit by bit by bit. Now, 2 main points. Firstly, deformation has progressed from the south to the north, as we see in this animation. Secondly, when blocks of the crust move towards each other, they very rarely do it in a directly orthogonal way. They usually are doing it oblique, as we've got here. Now, the block of crust that was Devon and Cornwall started life substantially to the southeast of its present position, and it moved sequentially up northwestwards until it met Wales and Ireland. And let's start this going now, and we can watch that happen. Now at that point, deformation has started to happen in the extreme south of the area in southern Cornwall with the emplacement of the lizard oceanic crust, and movement of this block is taking place along that almost southeast northwest strike slip zone that extends into the Bristol Channel that allows the whole of that block to move. Go on a bit further. Here you see Cornwall shortening, thrusts and folds developing, and the orangey brown colour indicating that deformation has increased in that area. And in the next steps you'll see Devon shortening and Somerset shortening, and structures appearing there too. Folds, anticlines and synclines and active thrusts, and by this time the structures in Cornwall had stopped working, so they're in an open ornament there. And onwards, Wales and Ireland now shortening, and here we have, just in Cornwall now, the emplacement of the granites. The state of deformation increases from north to south through the orangey browns into the deep brown of Cornwall. Now it's a simple model, if you like, sophisticated computer technology, but a simple generalization of how all those structures we've seen all fit together. We've looked at the Variscan orogeny in some detail, but most of them work in just this sort of way.